Good morning, students. My name is Robert Nguke. I want to take you on physics again, and the topic of today is physics in technology. So when we come to industries, physics is something that is applied in industry in all the technological processes, all the production processes, manufacturing, and in this particular class, we are going to discuss the mathematical aspect of physics. So when we come to the mathematics aspect of physics, it involves the direct proportion or variation and inverse proportion or variation, which I know people have done in mathematics. Now, specific objective. At the end of the lesson, students should be able to solve direct and inverse proportion, state the fundamental and derived quantities, state the fundamental and derived units, then state the multiples and submultiples. Then direct proportion. In a direct proportion, one quantity increases as the other quantity also increases. So that means the other way we say that increase in one quantity leads to increase in the other and vice versa. So that means when one quantity decreases, then the other one decreases. So now we say the increase or decrease may be by the same amount or size or slightly different amounts or magnitude. So, for example, if we say the quantity A is directly proportional to quantity B, then it means that quantity A increases as quantity B increases, or the quantity A decreases as quantity B decreases. Okay, now we look at it mathematically. For example, given that A is directly proportional to B, what is the relationship between A and B? We know in many areas of physics, we look at and make laws. We see two quantities being proportional to each other. So we see A is proportional to B. So that means A is equal to KB. So where K is the constant of proportionality. So at any point in time, when the sign of proportionality is changed to equality, we introduced a constant. A constant. The constant may be, in some cases, it may be a dimensioned constant, it may also be a dimensionless constant. I'm sure you have done dimension in your first term. So now in this case we say that K is equal to A over B. So that means if there is any change in A or B, there will be a corresponding change in B or A. So in the other way around, we can represent this particular proportionality by A1 over B1 is equal to A2 over B2. Then sometimes we also say A1 over A2 is equal to B1 over B2. They mean the same thing. Okay, let us look at an example. Let's look at an example. We say the amount of heat generated by a body is directly proportional to the mass of the body. Now, if 10 kg mass produces 25 joule of heat, now what is the quantity of heat that 15 kg mass will produce? Now, we look at the solution. So from the question, we see that it is a direct proportion. Then, the amount of heat is directly proportional to the mass of the body. So that is H is directly proportional to M. So we write it mathematically. You now have that H is equal to Km, where K is the constant of proportionality. So we can find a constant. This constant of proportionality, as the name implies, is constant throughout this question. It does not change, and it applies to both the initial condition and the final condition, because it is what? The constant of that particular proportionality. So we can just say K is equal to H over M and find it. Also, we can say H1 over H2 is equal to M1 over M2. So as we are given, we now see that M1 is 10 kg, H1 is 25 kg, M2 is 15 kg, while H2 is unknown. Then, since we now say that H1 over H2 is equal to M1 over M2, then we now have 25 over H2. 25 is the H1. So 25 over H2 is equal to 10 over 15. And that implies that H2 is equal to 25 by 15 divided by 10, which is equal to 37.5 joule of heat. Okay, now if it is inversely proportional, you know that the increase in one will lead to the what? The decrease in the other, and vice versa. So you can practice the question, the given question, considering it to be an inverse proportion. I don't want to dwell much on this because this is something you could have done in mathematics, just that it is necessary to introduce it as a part of what? The physics in technology. Okay, then we have physical quantities. Now we said that physical quantities are properties of substance or phenomenon that has a magnitude and can be determined and expressed from a reference point. That's physical quantity. So we see that physical quantity can be classified into two, as we know. We have the fundamental quantities and the derived quantities. So we say fundamental quantities, they are basic quantities and do not depend on any other quantity. So for their definition, for their derivation, fundamental quantities are basic. They don't depend on other quantities for you to define them or for you to derive them. So we say that they are quantities that cannot be defined in terms of any other quantity. So they are quantities that other quantity depend upon for their derivation. So for you to derive other quantities, so you must derive them in terms of the fundamental quantities. So now, what the fundamental units? Say the fundamental units are the units of fundamental quantities. They are the units of fundamental quantities. The basic units, the fundamental units we have them and their symbols. So number one, we have the length, which has a symbol L, and the unit is in meter, small letter m. We have time, the capital letter T, and the unit is in seconds, small letter s. Then we have mass, capital letter M, then the unit kilogram, kg. We have electric current, capital letter I, the unit ampere, capital letter A. Then we have temperature. We usually call it thermodynamics or absolute temperature. It is represented with theta. The unit is in Kelvin, K. And amount of substance, N. The unit is in mole. Then we also have luminous intensity. The unit is in candela. These are the fundamental quantities. Outside this, all other quantities are derived. Then we now have the derived quantities. We say derived quantities are those quantities that are derived or obtained from the fundamental quantities. So they are dependent quantities that depend on the fundamental quantities for their derivation. So the derived quantities are made up of combination of two or more derived quantities or fundamental quantities. Sometimes it is also when a given mathematical computation is done to the fundamental quantity, such as exponential, inverse, so you get a derived quantity. Then the derived unit. We say derived units are the unit of derived quantities. They are derived from the combination of fundamental units. So, like I said earlier, the fundamental quantities and their units are 7 in number. Then why the derived quantities and their units are numerous? They are uncountable. So we just give few examples of them. For instance, we have number 1, we have speed. Is measured in meter per second. We have velocity also measured in meter per second. You know, I am sure you know the difference between speed and velocity. Then we have acceleration. Acceleration measured in meter per second square. We have density measured in kilogram per meter cube. Area measured in meter square or square meter. Then volume measured in cubic meter. Then work. Work is measured in Newton meter, also known as joule. Then we have momentum. Momentum is measured in kilogram meter per second. So we have force. Force is measured in Newton, or in terms of the derived quantities, it is kilogram meter per second square. Kilogram meter per second square. Then we have pressure. Pressure is measured in Newton per meter square or kilogram per meter square. Kilogram per meter per second square. Sorry. Kilogram per meter per second square. Then it is also measured in Pascal. Pascal. Then we have the impulse. Impulse is measured in Newton seconds or kilogram meter per second. Kilogram meter per second, like that of momentum. Then we have frequency. Frequency is measured in hertz or per second. And we have a resistance. Resistance is measured in ohm or volts per ampere. Volts per ampere. Then we have a plane angle. The plane angle is measured in radians. Radian. While the solid angle is measured in steradians. Steradians. Now we see luminous candela. You know the luminous, that's luminous flux or just luminance. Luminance. So we say it is measured in candela per square meter. Remember, candela is a fundamental unit, the unit of luminous intensity. So here we say that luminance is in candela per square meter. Then power. Power is measured in watts or joule per second. Then we have electrical capacitance. Electrical capacitance is measured in farad. Is measured in farad. Then we have a current density. Current density. Current density is measured in ampere per meter square. Ampere per meter square. Then we have a specific volume. Specific volume is measured in cubic meter per kilogram. Cubic meter per kilogram. Then we have magnetic field strength. Magnetic field strength is measured in Tesla. Tesla or Weber per meter square. Weber per meter square. Then we have wave number. Wave number is measured in per meter. Per meter. So we have many other quantities that are derived. Then we now look at multiples and submultiples. These submultiples are used. They are used in measurement. So in physics and in technology, you find out that most quantities are measured in terms of these submultiples and multiples. For instance, when you want to measure a long distance, such as the distance covered by a man when traveling from town A to town B, you use in kilometer. That kilo there is a multiple of the meter, which is the unit of the distance. Also, when we measure a small distance, such as the diameter of a thin wire, the thickness of a paper, using precision instruments, then we see something like millimeter, micrometer. So that milli there is a submultiples of meter, which we know is the unit of the distance. So we see that the submultiples and multiples are used in measurement. When we are talking about a very small measurement, we use submultiples. But when we talk about a large measurement, we use multiples. So here, in the submultiples, we have milli. Milli is 10 raised to the power minus 3, which is the same thing as 1 over 1000. 1 over 1000. Okay, micro is 10 raised to the power minus 6, which is 1 over 1 million. The nano 10 raised to power minus 9, which is 1 over 1 billion. So we have pico 10 raised to power minus 12. We have femto 10 raised to power minus 15. We have atto 10 raised to power minus 18. We have many other submultiples. We have exo, we have iota, and so on and so forth. Then in the multiples, we have kilo 10 raised to power 3, mega 10 raised to power 6, giga 10 raised to power 9, tera 10 raised to power 12, theta 10 raised to power 15, exa 10 raised to power 18, and so on. We still have more multiples. We have that of 10 raised to power 21, 24, and so on and so forth. Okay, so these are the multiples and submultiples. Okay, so you visit the Google Classroom for your homework and assignment. Thank you very much for listening.